In constructing the fourth figure in the sequence, we should have no difficulty, although it is more easily shown than explained. Therefore, let us play a little game of show and tell. Of course, we need to show or to construct or to draw, represent the fourth figure in the sequence, and we make use of what we see there already. So the first pattern has a single square with its diagonals. The second pattern has two squares with their diagonals. The third pattern has three squares with their diagonals. So the fourth one will have four squares with their diagonals. Therefore, the fourth pattern will have four squares with their diagonals. There we have them. That's all there is to it. We need to complete the table for the rows that are indicated right there. 1, Roman 1 and Roman 2. And we are making use of patterns that we find in that table. The first number in each expression is the same as the number in the first column. So notice that we have a formula here, and in the first column the numbers are the same. Therefore, we'll imagine that we'll have a 4 and a 10 there. Therefore, in each row, the first number in each subsequent expression has to be the same as the number in the first column. So the number in the first column, the number in the first column, the number in the first column, and also right there. So 4 will be there, and 10 will be there. Anything else to notice? Yes. 6 is a constant value in each expression, so we always have 6 all the way down. So 6 goes there. And anything else to notice? The final number in each expression is always 1 less than the number in the first column. So we have 1 less than that is 0. 2, 1 less than that is 1. 3, 1 less than that is 2. Therefore, we expect to have a minus 3 right here and a minus 9 right there. And then the value that we get here is the result of calculating what we will get from these expressions. 4 6 is 24, minus 3 is 21, and 10 6 is 60, minus 9 is 51. So we'll imagine that we'll have 21 51. The third column has the equivalent of the expressions. 21 51, no problem. 4 6 is 24, minus 3 is 21. 10 6 is 60, minus 9 is equal to 51. And then what do we do next? The sequence starts at 6 and goes up by 5 each time. Consequently, the terms are related to the multiples of 5. So the first term is what? 6, which is 1 multiplied by 5 plus 1, which is 5 plus 1 is 6. What about 11? 2 times 5 is 10 plus 1. What about 16? 3 times 5 plus 1. So we notice that there's a constant going up like that by some multiple of 5. 5 1 5 plus 1 6. Then we have 5 2 is 10 plus 1 11. 5 3 is 15 plus 1 is 16. And then 5 4 is 20 plus 1 is 21. Therefore, 106 must be some number multiplied by 5 plus 1, which is what we are saying right here. And we can just say it simply because we are saying that 6 is some number multiplied by 5 plus 1, 16 is some number multiplied by 5 plus 1, 21 and also 51 is some number multiplied by 5 plus 1. There we have it. So 106 is equal to some number multiplied by 5 plus 1, or 5 times the number 5n plus 1 is equal to 106, and we need to solve that problem. So we subtract 1 from both sides, and then we finally divide by 5. So n is equal to 21. You see 21 here, you see 21 there, and you are tempted to say, how comes? But 21 is not the figure that we are talking about. The figure that we are talking about is this 21, which is supposed to be a number in this column, not a number in this column. The expression that we are required to write in D is the same as the one that we have right there, which is 5n plus 1. However, we will use the development of the patterns in the table to substantiate our claim. So this same 5n plus 1 we have right here is the 5n plus 1 that we have in the final part of the problem, but we will not just take it for granted. Although we have enough proof already, we will also take an algebraic approach to it on the next slide. The first number in each expression is the same as the number in the first column, consecutive counting numbers. Therefore, for the nth pattern, the first number in the expression will be n. What about the next one in the expression? 6. 6 is a constant value in each expression and will be present in this general expression also. So 6 will go there. And what else do we know? That the final number is in each expression is always 1 less than the number in the first column. In this particular case, it should be 1 less than n. 1 less than n is n minus 1. There we have it. Expand the brackets and simplify. Do not forget that the negative multiplied by negative will result in a positive. So negative multiplied by this negative 1 is going to be a positive. And what do we have? 6n minus n plus 1. 6n minus n is 5n. Put the like terms together, we have 5n plus 1, and that is what we discussed on the previous slide. In our previous presentation, there is a problem that is analogous to this one. It may be consulted for greater details in the solution of this problem. So this is problem paper number 13, and we have gone through quite a bit. The one that we have gone through is analogous to this one. It is not exactly like it in every single way, but the numbers are quite similar, and we will make use of the same pattern because, as a matter of fact, the sequence is very, very close, if not exactly the same.